Well, hello and good morning. um, uh, Chem 400. This is our penultimate lecture, which I've been saying as many times as I can over the past week. Penultimate means second to last. Whoa, hang on. There we go. Now we're muted. Heck yeah. Dude, Gregory, I I don't think you're the only one who's looking forward to putting the semester in the rear view. I've had two classes to handle: Chem 400 lecture, and then I teach a OChem lab. But you guys have had to, so that's I've had to juggle the transition of, you know, putting those two classes into the internet. But you guys have had to juggle all your classes being taken online, with every professor probably doing things a little differently. Very little consistency, and anyways, I imagine it's been harder for you than for me. So we're almost there. A week from Wednesday, you will no longer have online chem in your life. Okay, Raj, great question. Do we have lecture on Wednesday? We do. We do. So here is the plan. So for today, oh, that is a larger pen than I like using. Let's knock this down a little bit. So today, oh, that's a smaller pen than I like using. I think I like my brush around, yeah, like 23. Okay, so here's our plan. So for today, we are going to finish off intramolecular forces. And that's what IMF stands for, intermolecular forces. Totally. Diana, that is exactly how I feel. It has been brutal, but we are in the home stretch. Wednesday will be so we will have we will have lecture on Wednesday, but I will have nothing to lecture on. So Wednesday's class is going to be open office hours / exam review. All right, the kind of to get your last minute questions answered before diving into exam 3. And just as all office hours, you can email your questions. You can email any questions that you have ahead of time, or you can ask live. Either of those, obviously. You will have it will if you email your questions in ahead of time, it will have you'll have a better chance, not a better chance, but I'll prioritize. Sorry, some mornings English is harder than others. When you email your questions in, I'll make sure to hit all the emails. Just put make sure that your subject line is Chem 400 office hours, so I don't miss it. We have quite a tour de force this week, because today we're finishing intermolecular forces. Wednesday, office hours, last minute exam review, and then Wednesday to Thursday, you all will be taking exam 3. And then on Friday, we will have office hours at the normal time. 1 p.m. office hours. And this will give you a chance to ask any questions you may have about our final. Which I still haven't started working on because your exam 3 is done, both the take home and the multiple choice. I'm currently writing my lab exam for my lab class on Wednesday, and then once that's done, I'll start on the final. So anyways, that's what our week looks like. It's going to be a crazy last week. Let's go ahead and dive into our new material here. Raj, exactly what you were saying. We're going to be covering hydrogen bonding, and then looking at the effect these intermolecular forces have on the physical properties of compounds. All right, so we have covered, you'll recall, we said we're going to cover 3 intermolecular forces: London dispersion, dipole-dipole forces, and then hydrogen bonding. And it is time to talk about hydrogen bonding. All right, now, you'll recall that when I introduced dipole-dipole forces, I was like, well, it's kind of like London dispersion on steroids, right? You'll remember that London dispersion forces is an attractive force based on a temporary partial charge in an atom or a molecule. And hydrogen bonding, and then dipole-dipole forces is an attractive force based on permanent partial charges. Well, hydrogen, just like dipole-dipole is like London dispersion on steroids, hydrogen bonding is kind of like dipole-dipole forces on steroids. This is the next force we're leveling up. It's stronger than dipole-dipole. And to engage in hydrogen bonding, you need not an atom. You need a molecule that has 2 features. All right, there are 2 things you need for hydrogen bonding to be present in a molecule. All right, the first is somewhere in your molecule you need a lone pair. You need a lone pair of electrons. All right. It's one of the 2 things you need to be for a molecule needs to be eligible for hydrogen bonding. The second thing that a molecule needs is it needs to have a hydrogen directly bonded, directly attached you need a hydrogen directly attached to nitrogen, oxygen, fluorine, or chlorine. All right. If you have a hydrogen that is directly attached to one of these atoms and you have a lone pair somewhere in your molecule, then that molecule can engage in hydrogen bonding. Oh man, Diana, that is an excellent question. Excellent question. Here, hang on one second. Alrighty, sorry, I just had to step out to make sure that the 2-year-old was just being a 2-year-old. And turns out he was. He's okay. He's just has a lot of emotions right now. Anyways, okay, Diana, great question. I will. So the difference. Let me get back to you. Okay. Let's get through hydrogen bonding first. And then I'll come back and answer that question. Great question. Okay, so stay on the line. There's an answer coming for that. First, let's talk about hydrogen bonding. So you need these two features. You need a lone pair of electrons somewhere in your molecule, and you need a hydrogen directly attached to nitrogen, oxygen, fluorine, or chlorine. All right? And here's why. Okay, so here's what hydrogen bonding is. Let's look at hydrogen bonding in a molecule of water. Or between, I should say, two molecules of water. Now, we already know that so the electronegativity difference between oxygen and hydrogen is oxygen's 3.5, hydrogen is 2.1, so that is 1.4. That's our electronegativity difference, and that means that we're dealing with polar covalent bonds. All right, we're dealing with polar covalent bonds. And we know that that means that the electrons in these oxygen-hydrogen sigma bonds are unevenly shared. They spend more time around oxygen than hydrogen. And so oxygen picks up a partial negative, and each hydrogen picks up a partial positive charge. All right? Now, yes, Viraj, that is correct. In order to be able to hydrogen bond, the hydrogen atom needs to be directly connected to either oxygen, nitrogen, fluorine, or chlorine. If it's not, then that hydrogen cannot engage in a hydrogen bond. All right? Now, when you have water molecules floating around with each other, we already know that the oxygens are partially negative, the hydrogens are partially positive, and so the hydrogen on one water molecule will be attracted to the oxygen on another, all right? And so far, that attraction is just dipole-dipole forces. Let's see. Okay, just to review, is there only intermolecular forces? Great question, Vraj. So Vraj's question, is there only intermolecular forces when the bond is polar? So there can only be dipole forces when the molecule is polar. Intermolecular forces include hydrogen bonding, dipole-dipole, and London dispersion. So anytime there's electrons, anytime there's London dispersion, you do have intermolecular forces, but they're the weakest of the three. If your molecule's polar, you have dipole-dipole. If you have a lone pair and a hydrogen attached to nitrogen, oxygen, or fluorine, or chlorine, then you have hydrogen bonding. But intermolecular forces is present anytime any one of these three is happening. All right, so as we know, there is an attraction between the partial positive charge on the hydrogen of one water molecule and the partial negative charge on the oxygen of another water molecule. These two are pulled together because the opposite charges attract. Raj, only if the molecule is polar. Carbon dioxide has polar bonds. Oops. And no dipole-dipole. Sulai, that is exactly correct. Yeah. London dispersion always happens. So if I ask you what intermolecular forces are in this molecule, you got to make sure that London dispersion is always there. If London dispersion isn't part of the answer's wrong. So you'll always have LD. The question is, do you also have dipole-dipole? Do you also have hydrogen bonding? All right, so here we are. We've got this hydrogen and this oxygen that are attracted to each other. And so far, that attraction isn't necessarily hydrogen bonding, all right? Because when you have a partial negative attracted to a partial positive, that's what happens with dipole-dipole forces. Here's where things are different, all right? So we have here, the difference lies in the fact that we have this lone pair on our oxygen, our negatively charged oxygen. We have this lone pair of electrons, and this lone pair is not involved in a bond, all right? It's not involved in a bond, and it feels the partial positive on that hydrogen. And what it does is it starts reaching out towards that hydrogen because it wants to form a bond. It's two negative particles attracted to that partial positive on hydrogen, all right? And it's almost as if it starts forming a bond, all right? But it's not going to form a full bond, all right? Now, here's what's going on. We've all seen this before, all right? Oxygen, this oxygen, which I'm underlining in blue, is attracted to this hydrogen that I'm underlining in yellow, all right? But this hydrogen in yellow, the problem is, this hydrogen in yellow is already in a committed relationship to this oxygen that I've underlined in yellow, all right? The yellow hydrogen and the yellow oxygen are already in a committed bond. This blue oxygen wants to bond with that hydrogen. It's reaching out. It's attracted. It's giving that hydrogen attention. Here's the deal. The yellow hydrogen is enjoying the attention that blue oxygen is giving it, but it's not going to break up with its bonded oxygen. It's not going to break the bond between the yellow hydrogen and the yellow oxygen. So the yellow hydrogen's not leaving, but it enjoys being flirted with by that blue oxygen. It enjoys the attention. It'll let that blue oxygen do, girlfriend things or boyfriend things for them, but they're not leaving their committed relationship, all right? Essentially, hydrogen bonding is one atom teasing another, where one atom is giving it its electrons attention, but it's not willing to form a bond. It's not willing to commit. It's not going to leave its relationship for the other oxygen. All right? Raj, great question. It needs both. You need both a hydrogen attached to nitrogen, oxygen, fluorine, chlorine, and a lone pair somewhere in the molecule. Because to make a hydrogen bond, yes, totally. Hydrogen is a flirt in this situation. It's willing to receive the attention of those electrons, but it's not going to commit. All right, it's not going to leave its original oxygen. And that is the heart of a hydrogen bond. Yeah, totally. You've got the molecule, one atom teasing another atom, and that's just that. But the one oxygen still wants that hydrogen. So, yep, it's a love triangle. That is absolutely what it is, Raj. Okay, so this part right here in blue, or here, I'm going to draw a another hydrogen bond. I'm going to draw this out just so I can label stuff with more clarity. So I'm just going to redraw what we already had. All right, so here, these lines that I've drawn, these kind of hatched lines, this is how you draw a hydrogen bond. All right, so when I ask you to draw a hydrogen bond, that is what I'm asking for. That is the hydrogen bond. The two players in this molecule, or in this hydrogen bond, right? Because it takes two parts to make a hydrogen bond. The two players are labeled as, so the molecule that brings the hydrogen to the hydrogen bond, this is called the hydrogen bond donor, because it's donating the hydrogen. All right, so this will be the hydrogen bond donor. And then the compound that donates the lone pair, this is called the hydrogen bond acceptor, because it is accepting the hydrogen from the donor. All right, so if I ask you to draw a hydrogen bond, I'm asking you to draw the two molecules that are engaging in hydrogen bonding. And the one that's bringing the hydrogen is the hydrogen bond donor. The one that brings the electrons is called the hydrogen bond acceptor. All right? Okay. So, questions before now. I'm finally, Diana, ready to circle back to your question on what we've been talking about intermolecular forces. What are intramolecular forces, if there's such a thing? All right. Okay. So, Diana, that is a great question. Oh, let's see here. Hydrogen bond only happens between more than one molecule. Okay, Sulai, great question. So that's actually something that's true for all intermolecular forces. Occur between more than one molecule. All right. Because remember, intermolecular forces are the attractive forces that pull molecules together. So by definition, these are the forces that pull molecules together. They're what attract one molecule to another. So you've got to have more than one molecule if we're talking about intermolecular forces. Okay, and Raj, yeah, totally. Raj, let's see. Is there a case where H and H have no hydrogen bonds? So to answer Raj's question, you've got to remember, here's what you got to remember. hydrogen bonding only happens when you have both one a lone pair and two H attached to nitrogen, oxygen, fluorine, or chlorine. So there's definitely times where you'll have hydrogens in your molecule and not have hydrogen bonding. Yeah. LP is lone pair of electrons. Okay, so these questions have been excellent. Let's talk about the difference between inter versus intra. All right. Inter versus intra. Raj, great question. So the molecule contributing the H to the hydrogen bond is always the donor. All right, so inter versus intra. How many people out there listening on YouTube today have heard of something called the internet? Hopefully there's an ocean of emojis of people raising their hands. Hopefully we all know what the internet is. All right. We're all using it at least. But what it is what the internet is it is a network between all the computers in the world. Right, that is yes, that is the internet. How many of you have ever heard of an intranet? Not maybe not as many. Maybe some of you have heard of the intranet. There isn't, I actually can't say the intranet. I can say the internet because it's the whole thing. But an intranet is a network. It's a network between all the computers, all the CPUs in a company or institution. All right. It's a network that is all self-contained within one company. So for example, the way your grades are, your final grades are posted within the Los Rios, for the Los Rios Community College system, or not system. What's the word I'm looking for? District. Within the Los Community College district, I don't submit those to the internet. I submit them within their intranet, the network that is just an isolated network just for Los Rios users and computing. And it's an internal thing. It's not something that everyone everywhere has access to because it's only for use within the organization of Los Rios. So For example, intermolecular forces. Now, taking that idea, when we talk about intermolecular forces, that inter part means that we're talking about attraction between different molecules. So, for example, we could have two different molecules of HF, right? One of them having a dipole like this, and then another molecule of HF having a dipole that runs like this. And the attraction here this attraction, whoops, misspelling out the wazoo. All right, there we go. So this attraction is intermolecular. Whereas intramolecular if we're talking about intramolecular, which totally is a thing, is an attraction within the same molecule. Just like an intranet is a network within one institution. All right. An intramolecular attraction is an attraction within the same molecule, and you may be wondering how could such a thing happen? It's actually super common. For example, this happens all the time if you look at proteins. Like in biochemistry, this happens all the time. Because, for example, you could have a giant blob of a protein, which they always draw proteins as these like big cartoon blobs of nothing. And let's say you have an oxygen over here with a lone pair. And actually I need to give myself a little more room. I need a slightly bigger blob. But you've got a huge protein. And let's say you have an alcohol on one side and an alcohol on another side. And alcohol is an OH group. So we're getting a little organic chemistry here. And you've got a hydrogen bond donor and a hydrogen bond acceptor. So these two things can make a intramolecular hydrogen bond. Because one side of this molecule is attracted to another side of this molecule, and that attraction, because it takes place within the same molecule, is called intramolecular attraction. Ionic and covalent bonds are different, are actually different. So bonding is different than attractive forces. Oops. Attractive forces are like London dispersion, dipole-dipole, hydrogen bonding. There's a couple others that we haven't covered, so there are a couple different attractive forces that we haven't hit yet, but they're different than bonding. Bonds are what connect molecules together. Attractive forces are what makes one molecule want to hang out with another. Okay, so let's see. Oh no, I meant like they happen with both bonds, right? Okay, hang on. Oh, you're. Let me see, Raj. Are you asking if intermolecular forces happen with both bonding types? With does intra? Oh, okay. So, okay, here, hang on one second, Diana. Let's see. Ionic and covalent compounds. Ah, okay, awesome, Raj. Yes, the answer is yes. Totally. I don't know why I put a tilde there. I guess sloppy typing. Diana. Absolutely. Absolutely. To have intra molecular attraction, you need to have large molecules. So yes, so to have intramolecular attraction, you need larger molecules. So this happens quite frequently with organic compounds. It happens even more frequently than in like biochemistry. And as it turns out, you know how like DNA has like a double helix? Well, what holds those two strands together that helix are in the inside. You know how they always draw those like horizontal lines that are reaching towards each other? Those are hydrogen bonds that hold the two helices of your DNA together. So this stuff, you run into it all the time. Often in organic chemistry, like all the time in biochem. Raj, great question. Mostly because smaller molecules don't have the same they don't have the when you have a larger molecule, you can have different regions of the molecule, like, oh, this part's hydrophobic, this part's hydrophilic, whereas when it's a smaller molecule, there's basically just one thing going on. So you need more space, more atoms to develop intramolecular type of attraction. Is the short answer to that. All right, let's see. Totally. This stuff, Diana, this stuff gets crazy cool. Yep, Raj. The all of the nucleotide bases, straight up. Oh, there we go. Okay, let's see. Okay, how are we? Okay. All All right, we're actually doing. Oh, dude. Oh, Diana, you are going to fall in love with OChem. I just know you will, based on the type of questions you ask. And maybe if I'm lucky, I'll be teaching your lab section. Who knows? Okay, so that is hydrogen bonding. Now, there's a couple things that that I want to go over. One of the interesting things with so we laid out what a molecule needs to be able to hydrogen bond with itself. But one of the interesting things about hydrogen bonding is you do not need to be able. Okay, so we said that to engage in hydrogen bonding, you needed two things, right? We said that you needed first, you need a lone pair, and that second, you need a hydrogen. Oops, did not mean to draw that in blue. You need a hydrogen bonded to oxygen, nitrogen, fluorine, or chlorine. All right. And here's the deal. In order to experience hydrogen bonding with itself, a molecule needs both of these. All right. Because number one, actually, I'm going to swoop these down a little lower on the slide. If you have a lone pair, what that means is the molecule can be a hydrogen bond donor. Nope. Wrong way, sorry. Dyslexia makes life more fun. If you have a lone pair, it means you can be a hydrogen bond acceptor. And if you have, if the molecule has a hydrogen directly attached to oxygen, nitrogen, fluorine, or chlorine, it means that the molecule can be a hydrogen bond donor. All right. So if you're a molecule that meets both of these criteria, it means you can form hydrogen bonds with yourself. If you only meet one of the criteria, you can't hydrogen bond with yourself, but you can hydrogen bond with other molecules. Here's what I mean. So consider the molecule cyanide. All right. Lewis structure looks like this. All right. Now, if you look at this molecule totally has a lone pair, right? So that's good. But does it have an H on nitrogen, oxygen, fluorine, or chlorine? Totally does not, right? Fails this category. So that means that the molecule cyanide is capable of being an acceptor, but because it doesn't have a hydrogen on nitrogen, oxygen, or fluorine or chlorine, it can't be a donor. So it can be a hydrogen bond acceptor. Now consider the molecule, the polyatomic ion ammonium, which looks like this, NH4 with a positive charge. All right? Ammonium has no lone pair anywhere. All right? But ammonium does have an H on nitrogen. So it can be a hydrogen bond donor. All right? It can be a hydrogen bond donor, but it can't be a hydrogen bond acceptor. All right? Well, just because both of these molecules, both cyanide and ammonium, are not capable of forming a hydrogen bond with themselves. Cyanide can't hydrogen bond to cyanide because there's no H. Ammonium cannot hydrogen bond to ammonium because there's no lone pair. But cyanide and ammonium can hydrogen bond with each other. So if you had a solution that had both cyanide and ammonium present, one of your lone pairs on cyanide would hydrogen bond to one of the hydrogens on ammonium. All right? So this right here, again, is the hydrogen bond. Cyanide would be the hydrogen bond acceptor because it has the lone pair. And ammonium would be the hydrogen bond donor because it brings the hydrogen. All right. So something that I wanted to point out is to hydrogen bond with another molecule of the same type, a molecule needs both a lone pair and a hydrogen on nitrogen, oxygen, chlorine, or fluorine. But if both criteria aren't met, it can still participate with hydrogen bonds, in hydrogen bonds with other molecules that are not the same type. Does that make sense? So if you have a lone pair and no hydrogen on nitrogen, oxygen, fluorine, chlorine, you can be an acceptor. If you have a hydrogen on nitrogen, oxygen, fluorine, or chlorine, you can be a donor. And obviously, if you have both, you can be both donor and acceptor. Yeah. It's not too shabby, right? All right. So, yep. Sulai, I totally agree. I totally agree. Hydrogen bonding may be the strongest intermolecular force, but it's not the hardest. The conditions are fairly straightforward. All right, so now so we've covered them all now. We've covered all of our intermolecular forces. London dispersion, dipole-dipole, hydrogen bonding. We've got them all. How will I test you on these? All right. There's one very well, actually, hang on, sorry. I want to wait for a moment to comment how I'll test you on these, to make one final point. that would be a way to make it hardest. Now here's why intermolecular forces are important. All right. The intermolecular forces that a molecule experiences, intermolecular forces determine physical properties of compounds. Physical properties like melting point, which is abbreviated MP, boiling point, which is abbreviated BP, and melting point, boiling points, freezing point, which turns out is the same thing as melting point. FP. No, I'll just leave it at that. All right, all of these are phase transitions, right? They're when a molecule goes from one phase of matter to another. So, for example, melting point. When you look at what is melting point, it's when you have a compound go from a solid to a liquid. Right? It's solid to liquid. And when you think about the solid phase, you're I'm going to draw a picture because it's fun. So if you've got your beaker, you've got your stuff in the solid phase, all your molecules are packed tight together. Right? They're packed tightly together. They're a solid. That's where they're all sitting down there together. All right. In the liquid phase, all right, when a solid melts, in the liquid phase, the same number of molecules are not as close together. Right? They're flowing, they're moving, they're all over, kind of sloshing back and forth, right? They're not a hard packed solid. In the liquid phase, they are further away from each other. Than they are in the solid phase. All right. And the thing is, it always takes energy. It always takes energy to go from the solid phase to the liquid phase, because in the solid phase, all the atoms or molecules, all the particles are packed close, so they can feel their intermolecular forces because they're almost touching, right? Whereas in the liquid phase, you have to pull them apart. All right. And the stronger the attraction, the harder it'll be to pull them apart, right? You're going to have to put in more energy to separate them. The stronger the attraction is, right? So, for example, you can think of it as the difference between, like a, college age boyfriend and girlfriend show up to a party, and they're like hanging out, they're like holding hands, but they see people they know, they like move to different parts of the room. It doesn't take that much energy to separate them, right? There's an attraction there, but they don't like have to stick together, as opposed to like a super gross middle school couple like making out at the mall. Like the amount of energy to pull those two things apart, way harder, way more energy to separate that situation than an older, more mature relationship. That's the difference between a compound that has very strong intermolecular forces that don't want to be separated versus very weak intermolecular forces. All right. And so the point is the principle that you want to take away is the stronger a molecule's intermolecular forces, the higher the melting point, and this is also true, the melting point, this is true for boiling point, this is true for freezing point, the higher the melting point, boiling point, freezing point of that compound will be. All right. So the stronger the intermolecular forces, the more energy it takes to separate them, and that will result in higher melting points, higher boiling points, and higher freezing points. All right. That is the effect intermolecular forces have on those physical properties. Okay, Diana, I saw that you had a question a little bit ago, but now let me actually read it. Okay, so in lab, reacting two basic compounds like a salt and acid, the visible reaction. Oh, are we seeing? Oh my gosh, is the reaction we're seeing, the visible reaction we're seeing, hydrogen bonding related? So, oh man, Diana, that's an amazing question. So, turns out, let's talk about the reaction between an acid and a base. Let's talk about hydroxide to like HCl. We know what's going to happen here, right? We know that the base is a proton acceptor, and the acid oh man, that's awesome, is a proton donor, right? So the products of this thing are going to be H2O, which you'll forgive me if I draw it a little weird right here, and a chloride anion. All right, it's a base, and hydroxide's a base, HCl is an acid, and it produces water and the anion. All right. Now, what drives this reaction forward is a hydrogen bond. So what happens before the reaction even starts is you have this lone pair on hydroxide, which is a hydrogen bond acceptor. And you have this hydrogen on this chlorine, which is a hydrogen bond donor. And what starts this reaction going is the hydrogen bond acceptor, the lone pairs on hydroxide, reach out towards that hydrogen on chlorine. All right? And they start forming a hydrogen bond. Now, we said with hydrogen bonding, okay, we said with hydrogen bonding that the hydrogen likes the attention from those lone pairs. It likes feeling their presence there, but it's not going to leave its molecule to actually bond, right? It's kind of being a tease. Well, in an acid-base reaction, the hydrogen bond that forms is so good that the hydroxide, the hydrogen bond acceptor, actually does rip that hydrogen away from its original molecule. It takes it. They form a new bond. Yeah, it breaks up, hydroxide breaks up hydrogen with its chloride, and they form a new bond, new relationship, and chloride is left, well, rather negative after the whole experience. Yeah. So Diana, the heart of every acid-base reaction. The heart of every acid-base reaction is the story of a hydrogen bond gone off the rails. It's a hydrogen bond that went too far, that actually broke a bond with its original molecule and formed a new bond with the hydrogen bond acceptor. Totally. Totally. That's exactly what's going down. Awesome question. Okay. So, with that in mind, all right, and what I said before here, I'm just going to open up that slide really quick. The stronger a molecule's intermolecular forces, the higher the melting point, boiling point, freezing point of that molecule will be. Now I'm ready to talk to you about what you can expect on the third exam. All right, how you can expect to be tested on intermolecular forces. The first problem type. Exactly. Whoa, there we go. Exactly, acid-base stuff is rough, emotionally speaking. So how will intermolecular forces show up on exam 3? You're going to be seeing yeah, exactly. You're going to be seeing a couple different ways. I'm not willing to play my hand. There's one mystery problem on the written exam that pushes things a step beyond that I don't want to comment on. So I'm going to leave that one shrouded in mystery. But primarily, you'll see intermolecular forces show up in one of two forms. First, I could ask you to determine the intermolecular forces in ... and then I give you a compound. I could say determine the intermolecular forces in and then I give you a molecule. The second way that you'll see this show up is Raj, how about this? I'll tell you on Wednesday at 3 p.m. when the exam's open. That's what I'll so you'll know then. But okay. Something someone said in this lecture hit super close to home to the mystery problem. I won't say what or when or where or who, but yep. That's me. I am. No. You are the Batman. You guys all are the Batman. And I want to see you rise. If exam 2 was The Dark Knight, then exam 3 will be Dark Knight Rises by Christopher Nolan. All right. So, oh yeah, well, I was spilling some beans. Something someone said in this. They're like 40 robins, but I don't know. Oh my gosh, that's awesome. You guys are literally the best. Best Gen Chem class I ever had. Like, just straight up. You all need to know that. Okay, so intermolecular forces. I could ask you to determine the intermolecular forces in a molecule, or I could ask you to rank a group of molecules from oh uh let's see, from lowest to highest. I could say boiling point, freezing point, melting point. Um, Heck yeah. Okay, do you know what's weird? That movie is 12 years old. Um, that movie's over a decade old now. It was Mother's Day yesterday, right? And so my wife got to picked a movie that we all wanted to watch, and or that not that we all that she wanted to watch, and we watched it together. And she picked Super 8 by J.J. Abrams, and which I don't know if you've seen it. It's a great, uh, you know, kids mystery monster movie type thing. It's excellent. And anyways, we're watching it, and my 9-year-old goes like, we're watching it. He's like, "Oh, when was this movie made?" And yeah, totally. My 9-year-old was like 1 when it came out, and we told him, "Oh, 2011. Oh, you mean The Dark Knight? Yeah, yeah, yeah." So we told him, "Oh, this movie came out in 2011." And he's quiet for a little bit. We're watching, and there's this like scene where there's like this like explosion, and like the kids are running, and he's like, "Wow." My 9-year-old goes, "Not bad for a 2011 movie, for a movie that came out in 2011." And my wife and I just laughed because to us, it's a recent movie. To him, it's a super old movie. And anyways, nothing ages you like kids, I guess is the point of that story. But but it made us laugh. It turns out all of my cultural references are rapidly aging. Me too, Diana. I know, not bad for a 2011. Oh, we were dying. Okay, so anyways, let's talk about how I'm going to test you. The second way I think is a better way to do things. Rank a group of molecules from lowest to highest boiling point. Yeah, I know, Sula, I totally agree. And yes, 2011 was 2 years ago, and 2010 was like 4 years ago. You blink. You blink, and it's you know. And dude, here's what'll happen, because this is what's happening to me. You blink, and college is 10 years, is a decade in your rear view. That's what'll happen. All of you guys are in college right now, and it's awesome, and you're young, and you'll blink, and you won't feel that much older, but you'll realize that this whole experience, this coronavirus thing, happened a decade ago, and some of you will have kids, and yeah, totally, totally. Let me be the first to say that there are some great minds in this class. All right. How about an exam caliber intermolecular forces problem? How does that how does that sound? Sulai, that's a good question. I still don't know the answer. I still don't know when that happens. I feel very much like a kid who's raising kids. And it's this total mind trip because then it makes me wonder things like, because your parents are always your parents and your parents are always adults, and I know that's how like my kids look at me as like an adult and a parent and stuff, and I'm just going like, wait a minute, did my parents feel like kids when they had me? Like, are all parents just kids raising kids, and the only people who think that they're adults in the room are the kids, the younger ones? You know? It's weird. Life is weird. Yeah. Yeah. So, I'm faking it as best I can, and I think they're buying the act. We'll see how long this lasts. But anyways, here's an example that may or may not be similar to what you'll run into in 48 hours. Rank the following from lowest to highest freezing point. Sulai, that is the pure truth right there. All right, so rank the following from lowest to highest freezing point. And let me give you a handful of molecules. And how about this guy? And maybe this guy. We'll have a lot of lone pairs here. And then one final molecule, maybe formaldehyde. There we go. Okay, so rank the following from lowest to highest boiling point. So let's take a look. Now, in order to determine who has the lowest boiling point, who has the highest boiling point, we have to determine what intermolecular forces are present in each molecule, right? So really, this is an intermolecular forces, problem. One thing's for sure, whenever you're determining what intermolecular forces are present, you should always, right out of the gate, label each with London dispersion. All right. Everything with electrons has London dispersion, so everything experiences London dispersion forces. Now, the second thing we need to ask is, do we have dipole-dipole in the mix? All right. And in order to solve that, we need to take a look at whether or not we have polar bonds. All right. So for dipole-dipole, we need to look at the difference in electronegativity. Oh, hang on. So differences in electronegativity. There we go. So for carbon and hydrogen, and again, all these numbers, Raj, that is correct. All of these numbers, you don't have to memorize. In fact, on the cover sheet for the exam, I'm including a periodic table with electronegativity numbers in it, so you'll have that as a quick reference. Carbon's electronegativity is 2.4. Hydrogen's is 2.1. So here the electronegativity difference is 0.4. So that means that this is nonpolar. Nonpolar bonds. All right. If it has nonpolar bonds, then it's cannot have a dipole, right? So no dipole. And then when it comes to hydrogen bonding, there's no lone pair. All right. And there's no hydrogen on nitrogen, oxygen, fluorine, or chlorine. So no hydrogen bonding, no dipole, just limited dispersion. Now let's look at nitrogen. Nitrogen's electronegativity is 3.0. Hydrogen's is 2.1. So here we have an electronegativity difference of 0.9. That means we do have polar bonds. Right? Polar bonds. Just because you have polar bonds doesn't necessarily mean that you have a polar molecule. But if you look at this, we have 1, 2, 3, 4. So we're dealing with a tetrahedron. Whoa. We're dealing with a tetrahedral electronic geometry. And you have to ask yourself, do you have the same thing at each 4 positions? And the answer is no. So because we do not have the same thing on each position, right? If we had 4 H's, this would be nonpolar. But because we don't have 4 H's, we only have 3, this means that this is polar. So we do experience dipole forces. Finally, when we look at hydrogen bonding, we do have a lone pair, and, right, so we've got a lone pair, and we have a hydrogen bonded to nitrogen. So that means this molecule, Raj, like you pointed out, experiences hydrogen bonding. All right? So this one has all 3. Let's look at our next instance. So again, we look at the electronegativity difference between chlorine, which is 3.0, and carbon, 2.4. This comes out to be 0.6. It's on the smaller side, but we definitely do have polar bonds. All right, it's anything 5 or bigger. Polar bonds. All right, now, when you look at how many positions we have on our molecule, it's tetrahedral. And we have the same atom, we have chlorine in every position. So even though we have polar bonds, because it's symmetric, that makes this nonpolar. All right, so this is a non-polar molecule with polar bonds. So it doesn't have London dispersion. It also it does have lone pairs, but it has no H's bonded to nitrogen, oxygen, fluorine, or chlorine. So this third molecule has no dipole-dipole and no hydrogen bonding. All right. Finally, we've got two different things to look at here. We've got a couple bonds between carbon, which is electronegativity of 2.4, and hydrogen, which is electronegativity 2.1. Actually, I should probably do these in green. Carbon's 2.4, hydrogen's 2.1, oxygen is 3.5. Oh wait, let's see here. And actually, Raj, thanks for pointing that out. Chlorine, I messed that up. Chlorine's a 3.5. So this would actually be... And I think you are actually right. Carbon is 2.5. So let me fix those. So, Cl is also actually so it works out. Okay, looking at our last example, carbon and hydrogen, oh sorry, this should be 2.5. Come out nonpolar, but oxygen and carbon come out polar. Oops. So we do have a polar bond in this molecule. Oh, gave chlorine as 3.0? Let me double check. Maybe it did. Maybe I'm spacing out. Because I got something wrong here. Hang on. And what? Okay, hang on. Okay. Okay, right. Yeah, I see my mistake. Chlorine on this table is 3.0. Oops. Chlorine's 3.0, which would drop this down to 0.5. Okay, yeah. Sorry about the math mix up. 0.5 is still polar though. Oops. Whoa. 0.5 is still a polar bond, so we're okay. All right. Looking at our last one, we have a polar bond, but we have a polar bond, and you can see we have 3 positions in our trigonal planar central atom, and they don't have the same thing. It doesn't have the same thing at each position, which makes us, which means that we are a polar molecule. We do have dipole-dipole forces, and now let's look at whether or not we have hydrogen bonding. We do have a lone pair in our molecule, but you'll notice that we have no hydrogen directly attached to nitrogen, oxygen, fluorine, or chlorine. All right, we do have a hydrogen, but because it's not directly attached to nitrogen, oxygen, fluorine, or chlorine, we have no hydrogen bonding in this molecule. All right. So now that we've determined all of the intermolecular forces. Now we're able to determine we can rank these from the lowest to highest freezing point. Okay, here, hang on one quick second. So wait, why is the third one not dipole-dipole? Because, so Vraj, it's not dipole-dipole because, whoops, we have chlorine in every position of the electronic geometry. So all the polar bonds cancel each other out. They all cancel each other out. Oops. Just like in carbon dioxide. Okay, here, hang on 1 second. I need to step AFK for a second. My wife was texting me with for help with the baby. I will be back in like 1 minute, and then we'll solve this problem. Hang on 1 sec. Alrighty, okay. I am back. Sorry for that temporary interlude. Okay, now. So now let's rank these dudes. The slide got a little cluttered, so I'm just gonna redraw our are for candidates with their respective intermolecular forces. First, methane only has London dispersion. Ammonia has the trifecta, London dispersion, dipole-dipole, and hydrogen bonding. Carbon tetrachloride, which will take the longest to draw just by the sheer bulk of dots, only has London dispersion due to its symmetry. And then finally, formaldehyde has London dispersion and dipole-dipole. All right, so if we're ranking these from weakest to strongest, all right, so if I put weak or weakest or lowest to highest, lowest freezing point to highest freezing point. I'm just gonna give these numbers or letters. I'm gonna say this is A, B, C, and D. There's a far and away winner. There's a definitely the highest freezing point will be ammonia, right? Because it has the strongest intermolecular forces. So there's a clear winner. There's actually also a clear second place, right? Option D, which is formaldehyde, has London dispersion and dipole-dipole, so it has stronger intermolecular forces than both A and C. The question is, who's our loser? Who has the lowest freezing point and then the second to lowest? Because both of these, this looks like a tie, right? Because we are both only dealing with London dispersion forces, right? So who's going to win and who's going to lose, I guess. And the answer to answer that question, is you got to remember London dispersion is strongest or I should say stronger when orbitals, atomic orbitals, are larger. All right. When you have larger orbitals, there's more room for the electrons to move around, and it's easier for the electrons to both be on the same side of the orbital without repelling each other, right? So the larger your orbitals, the stronger your London dispersion. All right. And when you look at these, carbon is, has its valence electrons in an n equals 2 orbital. So these are the same, n equals 2. Hydrogen has its orbitals in an n equals 1, right? First principal quantum number. Chlorine has its valence electrons on orbitals where n equals 3. So because chlorine has larger orbitals than hydrogen, it means that carbon tetrachloride will have stronger London dispersion attraction than carbon tetrahydride. And so carbon tetrachloride, which is option C, will have a higher freezing point than a carbon tetrahydride. So whenever you find yourself painted into a corner with, you feel like you've got a tie, like, well, we've got two things that just have London dispersion. All you have to do is figure out, okay, well, which one has larger orbitals? Which atoms have larger orbitals? That will have stronger London dispersion, and that one will therefore have a higher freezing point, melting point, boiling point than the one with smaller orbitals. Cool? Alrighty. At this moment in time, so now, you know everything. Now you know everything. So you're ready for exam 3, right? I mean, to be honest, Raj, I can't remember. It's on one of them. Maybe both of them? I'm not sure. I have a diagnosable condition called test writer's amnesia. Right after writing a test, I can't remember what's on the test. I vaguely remember, but I'm not good at specifics. I know it's definitely on there, on one of them. I can't remember if I put it on both. Oh, excuse me, or just one. And I know that's not helpful because it doesn't actually answer your question. But I don't have an answer. No. You're like, there's 2 multiple choice. There's one multiple choice and one take home. Oh my gosh. Oh, Sula, you do that for me? That's so nice. What a nice thing to do for someone else. Oof. I didn't know what that meant till like a couple years ago. My kids had to teach me the truth of oof. Sorry about that. Raj is like, I want to help like that. That's the kind of help I'm the best at. For anyone still hanging on, we are officially done with lecture for today, which means that we are officially done with lecture for the semester. So at this point, I'm totally down to hang out. If you guys have questions, stuff you want to talk about, I am here and totally down. But officially, there's no more new stuff. You guys have all seen it all, which is quite a feat. You should give yourself a high five. you made it to the end of your first semester of general chemistry. I might as well take this moment to, if you're feeling stressed about upcoming events and need an outlet to chill, you should check out our daily mixtape. It's short and sweet, just four. It's actually not that short for it's 4 songs. Turns out 17 minutes of music. Just a nice, chill Radiohead playlist when I need to like kind of zen out, get into a calm headspace. I don't go to all of their discography, but definitely sections of it help me get there. So if you're looking to chill, the daily mixtape is for you. Will you answer questions on Wednesday? I will answer questions on Wednesday. And questions about Wednesday. Totally. All the questions on and or about Wednesday, I will answer. Maybe directly, maybe cryptically, but answers will be given. That much you can bank on. Totally. If nobody so I guess one question I have is are there any questions? Ooh, Richard, question. Okay. Quick question relating to grading homework 7 and 8. Sent you an email about it. Before the due date. Okay. Um, Richard. Dude, thanks for bring this to my attention. I am woefully behind on my emails right now. I will. Dude, so sorry for making you wait. But yes, I will thanks for bringing that to my attention. I will get on it and correct the mistake. I probably just missed it because if it wasn't in the main batch that came in. Oh, yep, there it is. Here, I'm actually Richard, I'm going to log into Canvas now and correct that before I forget again. So you should be seeing this correction relatively soon. I don't know how fast Canvas is with the updates, but I'm punching it in now, and it should be good. Oh yeah, totally. Oh yeah, no, dude, you're totally good. It was so my bad. Let's see. Let's see, get down to, there we go. Okay, Richard, I just punched him in on my end. I don't know how long it'll take for it to get reflected on yours, but as of right now in the official Canvas spreadsheet, you have credit for homework 7 and 8, which you totally did turn in on time. I just missed. Dude, Raj, I will catch you later. I hope you have an awesome... What is this? Today's a Monday. An awesome Monday. If there is such a thing. We'll see. Alrighty, well, I think this is where I'm going to put a pin in lecture for today. Again, study up, hit that hydrogen bonding stuff. You can see the post I made on Canvas about the exams if you haven't already. And come on Wednesday ready to discuss whatever you want. There is no pre-programmed lecture content. I will be taking any and all questions about whatever you need. Okay, sweet. Excellent. Oops. There we go. Dude, thanks again for bringing it to my attention. All right, and I hope you all have a totally awesome Monday. Look forward to seeing you Wednesday for our final class meeting together. I hope I'm gonna do everything I can not to sob into my microphone, because this has been in a lot of ways the hardest semester I've ever taught. But you have all made it worth it because you have been the best Gen Chem class I've ever had. So I'll catch you on Monday, and then hopefully sometime we'll see each other in the future wearing face masks, waving from 6 feet apart. I think might be the best we can hope for right now. Anyways, I'll see you all on Monday. No, I won't. Today's Monday. I'll see you all on Wednesday. Later.